Write down a number, any number, maybe your age, maybe your phone number, maybe how many people live in your city. Now let me ask you something. Does that number mean anything beyond what it represents? Does it change how you see the world? Does it make you question your place in the universe? Probably not. Numbers are just tools, right? They measure things, they quantify, they help us keep track. But sometimes, very rarely, a number does something else entirely. It doesn't just measure reality. It reveals something so profound about our existence that once you understand it, you can't look at the cosmos the same way. Carl Sagan found that number. Or rather, he helped create it. And it didn't give him answers. It gave him questions. Deep, unsettling, beautiful questions that he spent the rest of his life trying to answer. The number looks simple at first glance. It's not some massive figure with hundreds of zeros. It's not pi or the speed of light or the age of the universe. It's much smaller than that. And yet, this number, this one calculation, forced Sagan to confront something that most people never seriously consider. Are we alone? Not in the philosophical sense, not in the does anyone understand me sense, but actually physically, cosmically alone. Is humanity the only intelligent life in the entire universe? Or are there others out there, civilizations looking up at their own skies, asking the same question we're asking? The number Sagan worked with was supposed to help answer that. It didn't. Instead, it made everything more mysterious. Let me tell you what this number is and why it haunted him. In 1961, a scientist named Frank Drake organized a meeting. He wanted to discuss the possibility of finding intelligent life beyond Earth. Not little green men visiting Earth in flying saucers, serious, scientific extraterrestrial intelligence. Life that had evolved on other planets, developed technology, perhaps even built civilizations. Drake knew the question, are we alone, was too vague to tackle scientifically. So he did what scientists do. He broke it down. He turned a philosophical question into a mathematical one. He wrote an equation, a simple equation with 7 variables. And if you plugged in reasonable values for each variable, the equation would tell you approximately how many detectable civilizations exist in our galaxy right now. Not the universe, just the Milky Way, our home galaxy. That number, the result of this equation, that's what made Carl Sagan question everything. The equation itself looks deceptively simple. N equals R star times FP times NE times FL times FI times FC times L. Just multiplication. 7 factors multiplied together. But each factor represents something profound, something we don't fully understand, something we have to estimate, sometimes wildly. Let me walk you through it, because understanding what these variables mean is understanding why this number is so powerful and so frustrating. R star, that's the rate at which stars form in our galaxy. How many new stars are born each year? This one we actually know pretty well. Modern astronomy can measure this. The answer is roughly 1 to 3 new stars per year in the Milky Way. Not too shabby. Our galaxy is still making stars, still creating new solar systems, still giving planets a chance to form. So far, so good. This variable doesn't scare us. It's measurable, concrete, real. FP, the fraction of those stars that have planets. Again, we're getting better at this one. When Drake first wrote this equation in 1961, we didn't know of a single planet outside our solar system. Not one. For all we knew, planets might be rare, maybe our sun was special, maybe Earth was a cosmic fluke. But now, we've discovered thousands of exoplanets. Thousands. And the more we look, the more we find. Current estimates suggest that virtually every star has at least one planet. Some have many. So FP is probably close to 1. Almost every star has planets. That's good news if you're looking for life. More planets means more chances, more rolls of the cosmic dice. NE, the number of planets per star that could potentially support life. Here's where it gets interesting. Not just any planet will do. You need a planet in the habitable zone. Not too close to the star, where water would boil away. Not too far, where everything freezes. Just right, the Goldilocks zone. We call it that because it needs to be just right for liquid water to exist on the surface. And water, as far as we know, is essential for life, at least life as we understand it. How many planets per solar system are in that zone? In our system, arguably 3, Venus, Earth, and Mars. Venus is too hot now, but it might have been habitable once. Mars is too cold now, but it had liquid water in the past. Earth, perfect. So maybe 1 planet per system on average is in the habitable zone. Maybe a bit more, maybe less. We're still figuring this out. Now we get to the variables that make scientists nervous, the ones we can't measure, the ones we have to guess at. And this is where the equation stops being astronomy and starts being philosophy. FL, the fraction of habitable planets where life actually appears. This is massive, huge, because we don't know. We have a sample size of 1, Earth. Life appeared here. It appeared relatively quickly, actually, in geological terms. Within 1 billion years of Earth forming, we had simple life, single-celled organisms. So maybe life is easy. Maybe chemistry naturally leads to biology when conditions are right. Maybe every habitable planet eventually develops life. That would make FL close to 1. But maybe we're wrong. Maybe life is incredibly rare. Maybe the jump from chemistry to biology requires something improbable, some chance event, some cosmic luck. Maybe FL is 1 in a million, 1 in a billion. We don't know. We have no way of knowing until we find life somewhere else, or fail to find it despite looking everywhere. And this is where Carl Sagan started to feel the weight of uncertainty. Because if life is common, the universe is teeming with biology, microbes on millions of worlds, oceans full of strange creatures, forests of alien vegetation. But if life is rare, if Earth is the only place in the galaxy where chemistry became biology, then we're not just special, we're impossibly, incomprehensibly unique. And both possibilities are terrifying in different ways. But we're not done, because even if life appears, that doesn't mean it goes anywhere. Most life on Earth is still single-celled. Bacteria, archaea, simple organisms that have remained simple for billions of years. Intelligence is not inevitable. It might not even be particularly useful in evolutionary terms. Bacteria have survived longer than any other form of life, and they're microscopic and brainless. So the next variable asks an even harder question, Fi, the fraction of planets with life where intelligent life evolves. Define intelligent. We think we're intelligent, but are we the only intelligent species on Earth? Dolphins are smart. Octopuses are smart. Crows can solve complex problems. But none of them built radio telescopes. None of them developed mathematics. None of them can ask whether they're alone in the universe. So when we say intelligent life, we really mean technological life. Life that can manipulate its environment on a large scale. Life that can send signals into space. Life that could, in principle, be detected from far away. How often does that happen? On Earth, it took 4.5 billion years for technology using intelligence to emerge. And it's only happened once. 1 species out of billions. Does that mean it's rare? Or does it mean that once life gets started, intelligence is inevitable given enough time? We don't know. Sagan thought intelligence might be common. He was optimistic about this variable. He believed that evolution favors brains, favors problem solving, favors the kind of thinking that leads to technology. But he also knew that this was hope, not data, a wish, not evidence. And that uncertainty gnawed at him. FC, the fraction of intelligent civilizations that develop technology capable of communicating across interstellar distances. Okay, so you have an intelligent species. Do they build radio telescopes? Do they develop the science and engineering to send signals into space? Humans did, but only recently. We've had radio for about 100 years. That's nothing in cosmic time, a blink. And there's no guarantee we'll keep it. We could destroy ourselves. Nuclear war, climate collapse, technological catastrophe. Or we might just lose interest. Maybe civilizations develop technology and then move on to something else, something that doesn't involve shouting into the void. So even if intelligence is common, detectable intelligence might be rare. Maybe most civilizations never reach out. Maybe they can't. Maybe they choose not to. Another unknown, another guess. And finally, the variable that ties it all together and makes everything more complicated, L, the length of time a civilization remains detectable. How long do we send signals? How long do we survive? This is the variable that kept Sagan awake at night. Because it's not just about technology. It's about survival. It's about whether intelligent species can solve the problems that come with intelligence. Nuclear weapons, environmental destruction, resource depletion, artificial intelligence, bioengineering, all the things that could end us. If most civilizations destroy themselves shortly after developing technology, L is small, maybe a few hundred years, maybe less. And if L is small, then even if civilizations are common, even if they're popping up all over the galaxy, most of them are gone before they can talk to each other. They arise, they flourish briefly, they vanish. And the galaxy stays silent, not because there's no one out there, but because everyone keeps killing themselves. But if civilizations can survive their technological adolescence, if they can learn to live sustainably to avoid self-destruction, then L is large, thousands of years, millions. And if L is large, the galaxy could be full of voices, ancient civilizations that learned the lessons we're still struggling with, societies that have been around for so long they've seen stars be born and die. And if they're out there, if they've survived, maybe we can too. Maybe our problems are solvable. Maybe intelligence doesn't have to be a dead end. So now you see the equation. 7 variables, some we can measure, some we have to guess. Multiply them all together and you get N. The number of detectable civilizations in the galaxy right now. What's the answer? What's the number? That depends entirely on what values you plug in. And this is where it gets deeply, profoundly strange. If you're optimistic, if you think life is common, intelligence is likely, and civilizations survive for a long time, you can get numbers in the thousands, tens of thousands. The galaxy is bustling with intelligence, civilizations everywhere. Some older than ours by millions of years, some younger, some just now building their first radio telescope and wondering if they're alone. In this version of reality, we're part of a cosmic community. We just haven't made contact yet, but we will. It's only a matter of time. If you're pessimistic, if you think any one of those variables is very small, life is rare, intelligence is a fluke, civilizations destroy themselves quickly, you get a very different number. Maybe N equals 1. Just us, Earth, humanity, the only consciousness in the Milky Way, possibly the only consciousness in the observable universe. In this version of reality, we're it. We're the universe's way of knowing itself. And if we fail, if we destroy ourselves, the universe goes dark, at least in this corner of it. No one is watching. No one cares. We're alone in a way that's almost impossible to comprehend. Carl Sagan looked at this equation and he saw both possibilities, and he couldn't reconcile them. On one hand, the universe is so vast, 100 billion stars in our galaxy alone, 100 billion galaxies in the observable universe. That's 10 to the 22nd power stars, 10 billion trillion stars. And if even a tiny fraction of them have planets, and even a tinier fraction of those planets have life, and even a microscopic fraction of those develop intelligence, the numbers are still huge. There should be others. Statistically, mathematically, there should be others. But on the other hand, we've looked, we've listened, we've pointed our radio telescopes at the sky for decades. We've searched for signals, for patterns, for any evidence that someone else is out there trying to talk. And we found nothing. Silence. The cosmos is eerily, disturbingly quiet. No alien broadcasts, no evidence of megastructures, no signs of engineering on a galactic scale, nothing. This is called the Fermi paradox, named after physicist Enrico Fermi, who asked the simple question, where is everybody? If intelligent life is common, if the galaxy should be full of civilizations, why haven't we seen any evidence? Why the silence? There are lots of potential answers. Maybe civilizations are common, but they're too far away and radio signals degrade over distance. Maybe they exist, but they use communication methods we don't recognize yet. Maybe they're deliberately hiding, staying quiet for reasons we don't understand. Maybe they existed, but they're gone now, destroyed by war or disaster or their own success. Maybe intelligence is common, but technology isn't. Maybe most civilizations never develop radio. Maybe they never look up. Maybe we're early. Maybe we're the first, or among the first. And the galaxy will fill with voices in the future, but it hasn't yet. Or maybe we're alone. Maybe Earth is the fluke, the 1 in a billion chance that actually happened. And there's no one else. Not now. Not ever. Sagan couldn't accept that last possibility. Not emotionally. He believed, he hoped that we're not alone. He spent years working on SETI, the search for extraterrestrial intelligence. He helped design the messages we sent on the Voyager spacecraft, golden records containing sounds and images from Earth, just in case someone finds them billions of years from now. He believed that contact was possible, that communication was worth attempting. But he also knew the numbers. He knew the uncertainties. He knew that the Drake equation didn't give answers. It gave possibilities, a range, a question mark. And here's what bothered him most. The equation forced him to confront human nature, because that last variable, L, the length of time a civilization survives, that's entirely up to us. That's not astronomy. That's not biology. That's politics, ethics, wisdom. It's whether we're smart enough to not destroy ourselves. And looking at human history, looking at the wars we fight, the weapons we build, the environment we're destroying, the answer isn't obvious. We have the power to extend L, to make it thousands of years, millions, or we have the power to cut it short, to make sure we don't even reach the year 2200. And no telescope can tell us which path we'll choose. No equation can predict human behavior. The number that would tell us if we're alone depends on a number we control. And that's terrifying. Sagan wrote about this tension constantly. He saw the Drake equation not just as a scientific tool, but as a moral challenge. It was asking us, what kind of species do you want to be? Do you want to be the ones who survive long enough to find others? Or do you want to be another extinct civilization, another brief spark that flared and died in the cosmic dark? The equation doesn't judge. It just calculates. But the implications, the weight of those implications, Sagan felt that deeply. Think about what it means if n is large. If there are thousands of civilizations out there, that means survival is possible. It means intelligence doesn't have to destroy itself. It means other species figured out how to live with their own power. They solved the problems we're facing. They avoided nuclear war. They stabilized their climate. They created sustainable societies. And if they can do it, we can do it. Their existence, even if we never meet them, even if we never hear from them, would prove that it's possible. That intelligence has a future. That's hopeful. That's inspiring. That's the universe telling us, you can make it. Others have. You can too. But if n is small, if n is 1, if we're alone, that means survival is not guaranteed. It means intelligence might be self-limiting. A brief phase, a species gets smart enough to build civilization and technology, and then smart enough to destroy itself. And that's it. That's the pattern. If we're the only ones, maybe it's because everyone else failed. Maybe we're looking at a galaxy full of ruins, dead worlds where civilizations rose and fell and left nothing behind but radioactive craters and silent cities. Or maybe we're the first. Maybe we're the only ones who made it this far, which means everything we do matters, not just to us, to the galaxy, to the universe. Because if we fail, the experiment fails. If we succeed, we open the door for others. We prove it can be done. We become the ancient civilization that someone else finds in a million years. The ones who survived, Sagan oscillated between these possibilities. Sometimes he was optimistic. He'd talk about the billions of stars and the probabilities and the sheer vastness of space, and he'd say, they have to be out there. We just haven't found them yet. Other times he was darker. He'd look at human violence, at our nuclear arsenals, at the way we treat our own planet, and he'd worry that L is short, that we're not going to make it, that we're going to be one more dead civilization in a galaxy that's seen this story before. But he never stopped searching. He never stopped advocating for SETI. He never stopped believing that the search was worth it. Because even if we don't find anyone, even if the silence continues, the act of looking, the act of asking the question, that changes us. It forces us to think beyond ourselves, beyond our nations and tribes and ideologies. It makes us consider our place in the cosmos. It makes us think long-term. It makes us care about the future, because if there's even a chance that someone out there might hear us someday, we want to be worth hearing from. We want to be a civilization that survived. That solved its problems. That reached for the stars, not with weapons, but with curiosity. The number that made Sagan question everything wasn't a precise figure. It was a range, a possibility, a reflection of our own ignorance and our own choices. And that's what made it so powerful. Because it showed him that the question, are we alone, is actually two questions. One is about the universe. Are there others? The other is about us. Will we survive long enough to find out? And we can't answer the first question until we answer the second. We can't know if we're alone until we prove we're capable of lasting. And that's on us. That's not physics or astronomy or biology. That's human choice, human will, human wisdom, or lack thereof. So when people ask, did Carl Sagan think we were alone? The answer is complicated. He thought the universe is probably full of life. He thought intelligence might be common. But he also thought most civilizations might not last long, might destroy themselves, might never make contact. So the galaxy could be full of life and still seem empty, full of voices that never learned to speak to each other, full of potential that never got realized. And the question we should be asking isn't, are we alone, but will we still be here in 1,000 years to find out? That's the number, not the answer. The question, the uncertainty, the challenge. And it made Sagan question everything, because it forced him to confront the fact that we don't know. We don't know if life is rare or common. We don't know if intelligence is inevitable or a fluke. We don't know if civilizations last or collapse. We don't know if we're in a crowded galaxy or an empty one. We don't know if we're the first or the last. And we won't know, we can't know, until we either make contact or accept that we might be alone. And neither answer is comforting. Both are profound. Both change everything. So the next time you look up at the night sky, think about the Drake equation. Think about those 7 variables. And think about the fact that the most important one, the one that determines whether we're here long enough to find others, that one is up to us. That one is our choice. And maybe that's the real lesson. Maybe the equation isn't about aliens at all. Maybe it's about us, about whether we're wise enough to survive our own intelligence, about whether we can look at the cosmos, see how vast and ancient it is, and realize that our petty conflicts and short-term thinking are luxuries we can't afford. Not if we want to be the civilization that lasts. Not if we want to be the ones who finally answer the question, are we alone? Carl Sagan spent his life with this number, this equation, this question, and it never gave him the answer he wanted. But it gave him something more important. It gave him perspective. It gave him urgency. It gave him a reason to fight for a better future. Because if there's even a small chance that we're not alone, we need to survive long enough to find out. And if we are alone, we need to survive, because we're all there is, the only witnesses, the only consciousness, the only way the universe knows itself. And that's worth protecting. That's worth fighting for. That's worth questioning everything for.